So in this video, I'm giving you guys two proofs of theorem 2.7. Neither of those proofs is exactly the one in the book, but well, we can have some variety here. So what does the theorem say? The theorem says that if I have some graph G, there exists a larger graph H, possibly larger, it doesn't have to be larger, so that G is an induced subgraph of H. That means I'm adding vertices to G to get to H, and I'm adding edges to G to get to H, but I'm not adding any edges inside of G. That's what this means. I have a larger graph that contains G as an induced subgraph, means I can add vertices, I can add edges, but I cannot add any edges inside of G. To have an R regular, I have this graph H R regular, and the only restriction on R is that R is at least as large as the maximum degree of G, and of course that is a necessary restriction, because if we're not deleting any edges in G, then of course the maximum degree in G is that there's going to be stay in a vertex with at least that degree. So this is the picture, and now let's see how I could do that. So let's just give it an example and I'll show you. So here's my graph G, and let's say I want to make a graph which contains G, which is 3 regular. How can I do that? Well, I can add edges and I can add new vertices, and the easiest way to do that is to just add new vertices to G and connect them to the vertices so that every vertex has the degree that I want. And I want degree 3, so this guy here is missing 2 neighbors. Let's add them. This guy is missing 1 neighbor, 2 neighbors, and 2 neighbors. This last one already has 3 neighbors, so it already has degree 3. So we're done with that. And to finish this off, all I need to do is to make these new vertices have degree 3. How do I do that? Well, everyone already has degree 1, so all I need to do is adding a 2 regular graph to the green side, and I can easily do that by just putting a cycle into this. So I'm done. So does this always work? Well, what could potentially happen? Like, what could go wrong with this approach? Well, can I always add? I can always definitely do all these extra vertices and the extra edges. The problem, of course, is if I can always find this extra graph that brings up the degrees of these vertices to what I want. And, well, in this example, for this graph G, it will always work, but one could run into problems. One problem, of course, could be that, well, maybe this regular graph on that number of vertices doesn't exist. Because of parity from the last theorem, that one can actually figure out that cannot happen. But it could be that we just have to add too much here. Maybe we have to add a degree here for every vertex that is bigger than the number of vertices that I added in green. So how would we get around that? Let's look at an example first. Let's say here's my graph G. And again, I want to bring up everyone to degree 3. So if we want to bring up everyone to degree 3, there's only 2 of these vertices that are missing a partner. These 2. So everyone has degree 3 now, every blue vertex. And now we need to make the green vertices degree 3. This doesn't work because I cannot put a double edge between these 2 to make them degree 3. So what can I do? Well, I can just repeat this process that I just did there, and we can convince ourselves that this will always work because the green vertices only have degree 1, and no matter what I want to bring them up to, afterwards I have enough vertices to bring all of these up to degree 3, and I'm done. So this is essentially a first proof by picture. This is, and let's go. There's lots and lots of little things that one has to figure out here. This is a good idea, but it's a good proof, but it's a little bit hard to formalize. It has a lot of vertices, but not that many. Let's try to do something which is easier to write up, but may require a lot more extra vertices.